Hello, everybody, and welcome to another great day of chemistry. So today we're going to be doing a couple key things. So we're going to be diving into our first major unit, which is looking at gases. And when we're going to be doing this, I'm also going to start by talking about how we can build up different types of physical models and what our two major physical models are and how we can use them to construct the ideal gas law. We won't fi- We'll continue this process over the next couple lectures, but let's go ahead and get started. So when doing physical chemistry, there's two classical ways of building a physical model to describe a system. So the classic method, often known as the historical method or the empirical method or the experimental method, because it's often built from experimental data, is you go out, you grab some experimental data, and you fit the system to various predictive variables. So you identify what your key variables are and how they might control the system. And then you try and start building these sort of relations in between the two. So you first need to identify what are the variables that are related to the property you care about. And you're going to go ahead and measure those and often measure some response variables as well. Then you're going to try and connect all of the properties in a mathematical form. So we're going to try and build some sort of equation or model to describe the system. And then we're going to use this to build a little bit more of a broader theory to help describe what's going on. Now, once you've built that theory, you have to go ahead and test with more measurements, refine your model. And again, this is all built on starting with experimental data, try and model it, get more data, repeat the process. And this often provides a very good description of a system. So these often are relatively robust, but often they lack any origin for why the model works. The model instead kind of becomes a little bit of a black box. The model works because it works. Now, these methods are actually fairly good and robust, and they're actually relatively easy to build. And this is going to be the principal method we're going to be using this semester. And we can go ahead and apply this to a gas system. So a great example of how you build an empirical model is going to be the ideal gas law. And this is typically how you may have seen it derived in general chemistry. So you start by a series of relationships in between variables that we care about. So if I look at a gas, I can compare the pressure of that gas versus the volume of the container. When I do this, we're going to find an inverse relationship held together by a constant. And this is called Boyle's law. So the pressure of a gas is inverse to the volume. Decrease the volume, half the volume, double the pressure. Works great. Now we can do this for all the other variables. We can connect pressure to temperature, and this is Charles' law. So we go ahead and fit uh, a graph of pressure of a gas to temperature, and hey, we get a linear relationship carried together by some constant. And then we can do the same thing with the amount of gas, where we compare the pressure of the gas versus the moles of the gas present. And this is also a linear relationship carried together by some constant. Now, the pesky thing is each of these cases, while you're looking at pressure and volume, you have to keep temperature and moles of gas constant. And similarly, when looking at Charles' law, you have to keep the volume and moles constant. And for Avogadro's, you have to keep the temperature and volume of the gas constant. But when you do this, you can build up a nice series of relationships. Now we can go ahead and combine these together. So I know that pressure is inversely related to volume. We got that, and directly related to temperature and moles. So they go on the other side. And then these constants end up just devolving down into our ideal gas constant. So congratulations. Through three simple experiments, I can tie all of this together and get the ideal gas law. Refine it with data, and I can get a little bit better R. But that's a good example of how an empirical model works. And again, we're going to be playing a lot with these empirical models this semester. We're going to look at key variables, look at how they're related, and describe. And we'll try and go ahead and get some relationship of why they work as we go. However, the other major approach we have is called an ab initio model. So this starts on what's called first principles, which is where the ab initio comes from. So in this case, you start with basic chemistry principles, and then you keep adding additional features to the model based on logic. So this is often going to start with simple physics models. So you're going to figure out, all right, what are the most important feature of the model I want to try and describe? And then how would I expect these rules to apply and scale up? Now, worth noting, we're often going to start with a fairly simple system. So think about the classic joke about physicists with only treating spherical particles in a vacuum. It's a good start, but you often need to add some extra factors as we go. And we'll be doing that throughout the course of this chapter. But the beautiful part about these ab initio models, where they're a little harder to build, is we can really attribute the physical meaning and origin to each of these terms that we talk about. So this gives you a lot more explanatory power, but is a little harder to build up. So for example, if I'm trying to build up most of our chemistry models, we're going to start by assuming the existence of the atomic portions. So protons, neutrons, and electrons. Once I have that, I'm going to start applying either Newtonian physics, which is most of what we'll be doing this semester, or in quantum mechanics, I'm going to apply quantum mechanical principles. So once I apply these to my base components, we can start to build up a descriptive model. Then we verify against the experimental results. This will often give us our constants. And then we'll start applying more physical principles and keep refining the model till we get better results against experiments. So this is a little bit of a different way of approaching it. So what we're going to do is now rederive the ideal gas law from these first principles, and it will take us several lectures. And then we're going to use these same first principles rules and try and expand the model at the throughout the rest of the chapter. All right, so if I'm trying to derive an ideal gas law from first principles, we need to make a couple of key assumptions that will help really simplify our descriptions. So first one we're going to do is we're going to assume the gas consists of molecules with a mass m, where m is the weight of that individual molecule, and it's going to be constantly moving. Again, that should follow our basic rules, and it's going to obey Newtonian physics. So this is a really good approximation, and as we go, we're not really going to touch this one. It only breaks down under extreme conditions. Now, the next one is we're going to assume most gas molecules are really small and they're bouncing around in a really big volume. So that most of the time, I can treat these individual molecules as point particles. That means that their volume is really negligible. So we'll mostly ignore it. We'll bring it up here and there for some special properties. But generally, we're going to assume I'm not going to really care about the volume occupied by the actual molecules. They're small and space is big. Then our next one is that our molecules are going to more or less be bouncing around like billiard balls. So they're only going to interact with each other through elastic collisions. So this is the idea of, again, just uh, like pool balls bouncing around. When they smack into each other, they're not going to stick. They're not going to suddenly gain extra energy than they started with. They're just going to be bouncing off each other nice and simply. So again, all pretty good approximations, and they'll make a lot of our derivations a lot easier. Then, since again, as we saw with our previous model, we're really building up the ideal gas by looking at the pressure exerted. And this time we're going to assume that the pressure that I feel is going to be the pressure of that gas on the container wall. So now I have to imagine how will these little point particles be interacting with their container. So in this case, we're going to assume that they'll hit the container with a given force over an area of wall. So if we do this, then we can go ahead and use Newtonian physics. So force is just going to be the change in momentum over a change in period of time. So let's go ahead and start by kind of looking at what's going to be the change in momentum when a particle hits the wall. So in this case, the particle is going to be traveling with a velocity of v, And specifically, we're going to be keeping this in one dimensional. So just colliding with the wall in the X dimension and bouncing off in an elastic uh, collision. So if it's an elastic collision, if it comes in with a momentum of mass times the x velocity, it will have a mass times x velocity when it leaves. The only thing that will change is the sign. So the change in momentum is just going to be the sum of the difference of these two, which is just twice the mass of the particle. Okay, we know that depending on the identity of the gas we're dealing with. And then the velocity. Now this becomes a little bit trickier. So again, m is just the molecular mass, so not the molecular weight, so the mass per mole. This is the mass per individual molecule. However, this is going to be the amount of force for every individual molecule. But how many different of these particles are hitting? This is a little bit more pesky. So for this, what we're going to go ahead and assume is we're going to need to figure out the number of collisions or the number of particles that are going to hit the wall. So this is going to be the density of particles. So again, how many particles are in the container times the volume of gas that will hit the wall in a given time. So the density is just going to be the number, the moles of gas times Avogadro's, which again, just will give us the molecules of gas, divided by the volume of the container. Now again, note these will be a little bit different. And the volume of the gas that will hit the wall, which is not going to be the same as the volume of the container, but will be more or less highly related. So the volume of gas that will hit the wall is going to be the amount of gas that can hit it in more or less time t. Well, that's going to be based simply by the velocity times the time. So if a gas is moving very slow, it can actually be quite close and not hit it. But if it's very fast, it can actually be fairly far away and still hit. So this will essentially be saying, all right, we're going to be selecting for molecules of a given velocity that will hit in a time that correlates with that velocity. Works. Then we have to say, wait a minute, we're only going to be looking at half the particles because half of them will be going to the wall and half will be going away. And we only want the ones that are going to the wall. Now that gives me more or less the length of the box, but we also need to account for the area of the size of the box. So again, that will also show up here. Now let's go ahead and combine these equations for our volume and that for our volume and pressure. So again, the pressure is just force times area, which is just momentum over area times the time of collision. And again, the momentum is just 2 mass times velocity. Now we can go ahead and pair this with our number of collisions. So the number of collisions is going to be density times velocity, which gives us this nice, big, messy term where we get moles, Avogadro's, and V from the density, and the velocity time area and the 2 from the volume that will collide. Now, what we can do is this will be the pressure for an individual molecule. So the total pressure will simply be these two terms multiplied together. So the average pressure is going to be, wow, this is quite messy. But now we get this really beautiful little feature that terms start canceling. So we'll notice we'll cancel out the 2's. Works great. The areas also cancel. And hey, look, so do our delta t's. So this actually ends up giving us something a little bit nice. Another feature we have here is that notice the mass times Avogadro's number, so this is the mass of individual molecules times the moles, will actually correspond to the molecular weight. So this is the big molecular weight that we often think about, or that MW. So hey, that works great. So what we have is the pressure is going to be related to the weight of the gas times the moles of the gas present over velocity works, or over volume works great. And then this average velocity squared. Now, if we rewrite this, what we end up, where again, um, the big M is the molecular weight, and this Vx is the average velocity. Now, when we look at this, we have actually something quite pretty pop up. We have pressure times volume equals something of moles times something else. So this is already starting to look a little bit like the ideal gas law. The problem is, to make that last step, we have to figure out what is the average velocity of a gas. And that's a little bit more complicated. So we're going to go ahead and dive into that next time. Until then, take care.